Swayam Prabha. Digital India. Educated India.
Okay, so we've looked at the non-sway amplifier B1, side sway amplifier B2. Generally, we want to try to put them together and use them together to get solutions. So let's kind of spend a little bit of time looking at that. We'll do some things that relate that to doing more of a general purpose analysis. Obviously, if you're going to run second order analysis in consteel, you don't need B1 and B2. But I think one thing that hopefully you get a good impression of is, B1 and B2 can be useful still just simply to have a handle on what sort of characteristics of my system do I have. There's at least one software package out there I'm aware of. It was called Fast Track. I'm not sure how much I think they were trying to make some inroads in the U.S. a number of years ago. I don't think they've been too successful with that. But they actually had a portion of their system where it was very tied to, we're doing a general purpose analysis, but now we're calculating your B2 and everything, and so you can kind of understand what your system is doing, right? And then we'll look at a few cases that I think are very useful in terms of understanding behavior more broadly relating to side sway stability and combinations of both P small delta and P large delta. So I'm not going to spend much time or any time with this slide. This slide essentially just summarizes very tersely characteristics of a few different ways of putting B1 and B2 together with getting solutions. Okay, I'll focus on explaining what is on this slide in the slides that are coming. And to illustrate the methods, and a big part of what I want to illustrate here is there's some ways of doing the calculations that can be very streamlined, very efficient, work very well for certain frames, and for other frames you don't want to do that or you're going to be in big trouble. And this frame you see here is a good example of this. This is what I mentioned yesterday as Lemessurier's market shed frame. It's his third example in his 1977 seminal paper, but converted to where we're using it with an LRFD loading. So it's an ASC 7 LRFD loading of a maximum roof live load with dead and wind. And so the loads you see here are the factored loadings from that load combination. We've got a reasonably lightweight wide flange column on the left, reasonably deep roof girder on the frame, and this market shed, so to speak, the measure would say, on the right is storefront, so we have a very light HSS column there, and we're going to idealize that as a leaning column here in this analysis. Okay, all right, so now for the solutions we're going to do, I'm going to work the analysis according to the rules in AISC of what we call the effective length method of design, which basically means it's very similar in many regards to what you have in the Indian code, in my best understanding. You need to get a buckling load of the members to then get design strengths. So that's the effective length part, or buckling analysis based part. You're getting second order results in order to get your demands on the frame, but you're doing the analysis all with nominal stiffness. And for gravity only load cases, we would include notional lateral load. We'll talk more about that later. But this is a lateral load case. There's no notional lateral loads that would be required. So let's look at analyzing this load combination on Lemessurier's frame with different ways, where we do a first order analysis and then combine that with the amplification factors to get our total demands, our second order forces for design. So a very popular approach in the Americas, I don't see it from, I don't know if I missed it or not in the Indian standard, but it's something we call a no translation, lateral translation analysis. And this shows up in the AISC specification, but if I go over to the ACI code, it's very similar equations for pretty much doing first order analysis with amplifiers to get second order effects there. So for starters, let's say we did a structural analysis on the frame I just showed you. And so in that case, this frame would have a lateral deflections like you see shown in the dash lines and moments. Clearly the dominant moment is actually in the roof girder, but those small moments in the left-hand lateral load resisting column are of course very important. Now I tell my students at Georgia Tech, well, if you go to Cambridge, Massachusetts to interview with LeMessurier and Associates, you may want to bone up on this frame and be ready. They might put it in front of you and ask you to explain what's going on. The one thing that maybe is important to understand is if we take away the lateral loading for a second, if there wasn't any lateral load there, this frame would still have a significant side sway. Does that make sense? So why? So related to that, would I have any thrust at the foundation? Usually if I have a portal frame and I put gravity load on the roof, I got equal and opposite thrusts at the foundation, right? Any thrust here? What's going on with the column on the right? It's a leaning column. So can't take any shear? Right. Yep. So, but if there's no lateral load, there's no lateral load. So, but there would be no thrust, right? Because the leaning column cannot develop any shear, right? That's basically what you were saying, I think. Does everybody see that? We need the mic so we can, yeah.
So there is inequality in the boundary condition, and so when I take that as a pin joint at the right beam column joint, and then draw the bending moment diagram, I will. I think I just.
Yeah, if you take the horizontal load away, what would be the bending moment at the left-hand end of the beam?
So yeah, it will be 0 at the bottom, and there will be internal bending moment
for LeMessurier and Associates
at the beam column.
Yep.
So yeah, that's how the bending moment will come.
Right.
So I think.
Yeah. So under just vertical load, the bending so the 54 kilonewton meters on the left would go away. That's 0.
No, no. I'm not saying it will be 0.
Okay, go ahead.
Yeah, I'm just.
You might be thinking of the second order effects. So here, yeah, let's walk through it. So because the right-hand column is a leaning column, it cannot develop any shear. Okay? Since it can't develop any shear, it can't develop any end moments. It's what we call in statics a two-force member, right? And so whatever you do, the moment at the right-hand end of the beam is 0. There's no thrust coming from the column on the right. And so if you have gravity load, if you're just doing your first order analysis, well, if I have no thrust in the right-hand column, I have nothing to equilibrate any thrust in the left-hand column, correct? So I have to have zero shear, 0 moment in the left-hand column also. And my moment diagram is simply supported beam moment diagram in the roof girder, right? But for the left-hand end of the roof girder to rotate as a simply supported beam requires that the frame has to shift to the right under the gravity load. Okay. And here it's just a dinky little market shed. But as I mentioned yesterday, the Lake Placid ice skating arena where the U.S. Hockey team beat the Russian national team back in the day, that is a similar type of system. We could sketch that out similarly. The only difference is the ice skating arena at Lake Placid, the column on the left would be the same roof height, but a relatively short column. So now you end up with a very interesting system where that short column, since it's short, you get a sway, you get a very big P large delta effect because of the short length of that column. So some very intriguing things that are going on here with this frame. And this is kind of the poster child of examples where that can essentially, I'll say, break some of the simple ways that we often like to use B1 and B2. So that's the nature of this frame. Now let's look at what NTLT means with the structure. So again, this does this show up in any of the Indian standards, NTLT analysis? I wasn't able to find it in IS 800. No? Okay. So again, it shows up in the AISC specification and also shows up in the ACI specification in the Americas.
There's a clause that says.
Okay.
So
All right.
they cover.
Right. Yeah, I think there's a lot of specification committee members in the U.S. with AISC that would like to just throw this out of the AISC standard also and say that's a textbook thing. And then another group of practicing engineers will say, no, we should have that in there. So it's been staying. All right. So NTLT means we're going to first artificially restrain side sway. So we put in artificial or hypothetical supports at each of the story levels. Just one story here, but it could be multiple stories. And so we place the gravity load on the structure, but holding each of the floors to prevent side sway. So we're going to get a reaction at those floors, a reasonably decent reaction here, 40.41 kilonewtons to prevent this from swaying to the side. And of course, if we do this, now we can develop a shear in that column on the left, and we'll get some negative end moment, 146 kilonewton meters on the left-hand end of the roof girder. Well, at the LT part is we're going to say, okay, well, take the negative of the reaction in your hypothetical supports that were preventing side sway. So you're applying that reaction in the reverse direction along with any lateral load that's on the system. Analyze the frame first order analysis for that. That's your LT analysis, lateral translation. And clearly, if you add the analysis results in the bottom sketch to the ones in the middle sketch, you get the top sketch, right? The sum of the two bottom sketches is statically equivalent to what we have in the top, the actual structure. So these are all first order analysis results. And what do we do with them? And so LeMessurier again gets the credit for this. You apply your B2 amplifier to the LT moments. You apply your B1 amplifier to the NT moments. Now, generally, those may be at different locations on the column. Here's where we do an approximation. We'll just say, let's take the two maximums and add them. Then we'll take that as our estimate of MU for the column. So that's NT, LT. So we need a few things to put this together. For this frame, given what I showed you with the dimensions and the member sizes a few slides ago, we need a lateral stiffness. Well, you could get a lateral stiffness given the wind load that I showed you, or it doesn't matter what the lateral load or the story shear is. What's the deflection? Okay, the stiffness is load over deflection. So let's hit it with a unit load. It would displace by 1.171 millimeters under that unit load here on this frame. And so we can calculate the story stiffness, PL story, here from that. 1 times the story height divided by that side sway deflection. So PL story is 3,074 kilonewtons per radian. Radian story drift, or drift ratio. And then let's total up all the vertical load that's being supported by the frame. Well, we had a 60 kilonewton per meter load on the roof girder. The girder is 12 meters long, so we got a total of 720 kilonewtons being supported by this frame. All right, with the procedures with the P large delta with side sway that we've just been walking through, we need the R sub M. And for this frame, there is generally an overturning effect that you get if you have a lateral load on a system like this. It changes your column axial forces a bit. But a reasonable approximation here is that the column on the left is a moment frame column, and it's taking half of the vertical load, approximately. And then P story is the total vertical load. So PMF over P story is essentially 1/2 here, just a simple approximation. So I get an R sub M of 0.925. Remember, R sub M is accounting for it's generally a conservative estimate of the P small delta effects on the large delta. So now let's put all this into the equation we derived for B2. We get a side sway amplifier of 1.34. Okay? So we're going to take this both as the amplifier for the displacements and as well as for the moments, the side sway moments. Now we need to get B1. So for B1, we've only got one column here. Nice example, just one column. That's a lateral load resisting column. So our W200 by 71 column. Now I could calculate a K1 factor. For that, I would use the NT analysis. I would do a buckling analysis on that and get a K1 that would be less than 1 for that column. But I can tell you right off the start, I know I'm going to get B1 equal to 1 for this frame. In fact, I know it so well I don't even have to calculate it. But I'll demonstrate it here. Since I know that, I'm just going to be conservative and use K1 equals 1. Okay, if I was going to get a B1 larger than 1, okay, if I'm conservative, getting essentially a smaller PE1, then with a K less than 1, I would if I'm going to get anything larger than 1 for B1, I'll get it. So 667 is the non-sway or braced elastic buckling load of the column on the left. And so we put this into the B1 factor. I'm not showing the equation for CM, but this is the CM equation that's 0.6 plus 0.4 M1 over M2. And M1 is the base moment, 0, so CM is 0.6. Well, we end up with 0.62 for the amplifier, so we take that equal to 1. All right, so now we're ready to put things together. We take our first order analysis results from the NT analysis, first order analysis results from the LT analysis. We combine them. B1 times MNT plus B2 times MLT in whatever column I'm looking at. I'm looking at the column on the left here. I get my estimate of the maximum moment in that column. It would be at the top of the column, 122 kilonewton meters. And if we just ran this in Consteel or any other program that's a general purpose program and we get an accurate solution, it's not too hard to get an accurate solution for this. The rigorous solution is 115. Oh, it's conservative. Right, this is coming mainly from the conservatism of R sub m. If you think about it, if you look at the deflected shape, we had a few slides back here, that column on the left is not bending very much in this frame, right? So I'm not going to have much of a P small delta effect in that column. And so the R sub m tends to be conservative with something like this. All right? If I want to estimate, say, the moment at the midspan of the beam, it's the simply supported moment plus 1/2 of the moment that's coming in from the column on the left-hand side. So 1,141 foot kips, and the exact is 1,138. So not too shabby for a hand method. All right, that's the NTLT method of using first-order analysis with amplifiers. One way that's of doing things that's very popular in U.S. practice is to just say, well, just take the maximum B1 and B2. Usually it's B2 that's going to be the larger number, and multiply your first order moment from that, and just your ordinary analysis that you would do of the frame if you were given, here's the frame, do a first order analysis. All right, so 1.34 is our maximum amplifier. B1 is equal to 1. 54 kilonewton meters is the maximum moment in the column. I get 72 kilonewton meters. That's a bit of a problem. The actual moment is 115. What's going wrong here? Why is this not working? The issue is whenever you have side sway under the gravity load, or due to the gravity, when you get side sway of gravity load on the frame, if you're going to work it this way, things fall apart. If I've got symmetrical gravity loading on a symmetrical structure, doing this is fine. In fact, that's a very quick way to do it. It's a preferred way to do it. But you got to be careful if you've got, this is the extreme in terms of side sway under gravity load. Yeah, you don't want to do this. Another way that is kind of a near cousin of what I just showed you is to basically say, okay, I'm working in my design office. I'm going to do a gravity load analysis on my structure, and I'm going to do a lateral load analysis on my structure. Well, let me just take the gravity load analysis and hit that with B1, the results from that. I take my lateral load, hit it with B2, I get the same result. Since I don't have any gravity load moments here in this case, in my first order analysis, is up at the there in the middle, the analysis in the middle. Yeah, it's actually 115, so I'm significantly underestimating the moment if I do it this way. And perfectly fine to do this if it's symmetrically loaded in a symmetrical frame. Third method actually is a method that works pretty well, and this method, I call it the amplified story drift method. But if you're familiar with the literature, there's a lot of literature out there that refers to different ways historically of doing what we call a P large delta analysis on a frame. In an earlier time, when the computer use wasn't so prevalent, and you'd just be working with first order analysis of frames, you'd you have your frame, you get your lateral drift, and then there's ways of iterating a P large delta analysis to then get an estimate of your second order side sway effects. This is a non-iterative P large delta analysis, basically, in that sense. What am I going to do? I run my first order analysis on the frame, ordinary first order analysis. Nothing fancy. Just analyze the frame. I get my drift. So my first order drift here in this frame is 64.94 millimeters. I calculate my side sway amplifier B2. Okay, we've already done that. That was 1.34. And so that means, well, my actual second order drift is 1.34 times 64.94. It's actually drifting 87.02 because of the P large delta effects on the structure. So now we looked a little bit at P delta shears in a leaning column earlier. This is basically a P delta shears or equal and opposite shear forces you can apply at the top and the bottom of the columns of your story to create the same effects as your P acting through your delta, your vertical load through the delta. How can we do that? Well, we take alpha P story times delta. That's the total story P acting through the side sway, the second order delta. Divided by L, that would be a P delta shear force that relates to that. So that P delta shear, again, will produce the same lateral moments in the frame as your story vertical load, P story times delta. So that P delta shear, HP delta, is 17.4 kilonewtons. What we're going to do next is we're going to do another first order analysis of the frame where we're going to apply that P delta shear. Okay, so we get an additional moment of 63 kilonewton meters. And now we're going to we're basically going to sum those effects. I think maybe the graphic on the left there at the bottom is the same as the graphic at the top on the left, except I'm not saying these are second order results. So if I sum 54 and 63, I get 117. That's my estimate of the moment at the top of the column. Now, typically in a sway frame, more often than not, your B1 factor is going to be equal to 1, so that's very simple. And what we're going to do is you can see what we're doing is, well, in general, if B1 was not equal to 1, we would do 54 plus 63 gives us 117, and then I multiply that 117 by B1, just to cover the bases with any P small delta effects in the column. Here B1 is 1, so that's simple. Okay, 117 is still a little conservative. The rigorous analysis using, say, Consteel or another program would give 115 here. Why is it conservative? Because R sub M has some conservatism built into it. And how about the moment at the midspan of the beam? Well, that we can just get from statics, given the end moment on the left and end of the beam. That's 1139. Well, the exact is 1138, so not too shabby. And this is a non-iterative. This is basically a non-iterative BP large delta analysis, if you are familiar with some of the things in the literature from that. So advantages: we're applying B2 just to the story drifts, nothing else. All the second order beam, connection, brace, panel zone, beam column forces are obtained by just doing these two first order analyses and superimposing, applying amplifiers. In terms of a stiffness-based B2, I can say, well, I'm worried about my panel zones. I want to include that in my model. And so I include a panel zone deformation effect on my drift. Or I have, my column is short and stubby. I'm going to get some significant shear effects on the sway from the column. I include it in my model. So whatever it is, you've got a story stiffness, then work from there. And it's very general way of applying these simple amplifier equations. We're not messing around with applying separate amplifiers to different first order effects, NTLT, so no separate NTLT analyses. And it tends to give a little bit better accuracy in general than the NTLT approach. Again, it's simply just a traditional P large delta analysis, but using the amplified story drifts, so there's no iteration. What are the disadvantages? I've got to run two first order analyses, one for the actual loads in the frame, a second one where I put on the P delta shears in each story. But that's not too bad. Or just build your model and run it in your favorite software. And, well, what about B1 and B2 then? Well, again, they give us some indication of how the frame is behaving. So they're still useful in that respect, but we could easily at this time in our profession, second order analysis is relatively ubiquitous. for frames. And so, okay, use it. Now there can be some trickiness here if we start looking at three-dimensional structures. So I'll just say a few words about three-dimensional structures. And this is in the commentary to the AIC specification. Does anybody use RAM frame here? Is RAM frame used in India at all? They're based out of California, and they're quite popular in the U.S. One of their senior engineers has been a good friend on the technical committees of AICs for years. He just retired this past year, and he first started coming to technical meetings because he and one of the senior engineers for RISA were giving some presentations at the North American Steel Construction Conference, and they were kind of not being very kind in some of the words they were saying about how the recommendations in the specification were working for them. And so the director of AISC said, okay, so you've got these comments. Actually, what you're saying there is a little unfair, I believe. You kind of aren't on the same page in terms of seeing why we're doing some of the things we're doing, and why don't you come to the technical committee meetings so we can all talk about these things and it'd be better for everybody. So he started coming to the meetings. Shankar Nair was the chair of this particular technical committee, and we were having some discussions, and the engineer is explaining how in RAM frame they essentially use an NTLT analysis, but they have it coded all within the system, and how that can be they've got it set up so it's very efficient for doing design of steel frames using RAM frame. And it's a very popular product in the U.S. And he's explaining this, and Shakar says, well, that's not right. So we're going to have to fix this. Alan fixed it in his software, and this went into the commentary of the specification. So if you've got a 3D frame, you generally have to select some orthogonal X and Y directions. So you'll see a frame here where maybe the principal axes of the structure aren't so nicely aligned with the orientations of the columns. So we got an X and a Y. So then we're going to do our calculations. We need a separate B2 values. We need a B2 for side sway displacements in the X. We need a separate B2 for side sway displacements in the Y. And they depend on the total vertical load, but they also depend on the side sway stiffness in those two directions. And so then how do we apply it? We have B2 capital X applies to all forces produced by story translation in the X direction. B2Y would apply to all the forces produced by story translation in the Y. And so notice in a structure like this, B2 capital X and B2 capital Y, they're associated with the global axes that we've just selected, X and Y. That's completely unrelated to the axis of bending of the individual members. In other words, if we have a load in the capital X direction, it generally would cause both weak axis and strong axis moments in a given column here. And so B2 capital X would apply, we get M little x, M little y moments about both axes. B2 capital X applies to both of those moments if they're generated by displacement in the global X direction. So we would also need to apply separate B1 values, B1 lowercase x and lowercase y. So lowercase x and y are associated with the X and Y axes of bending of the individual members. Okay? And B1x would apply to M little x regardless of whether it was a drift in the capital X or capital Y causing it. Same thing for B1y. So that's how RAM frame now puts all this together. I think you can probably see from that, the hand waving I've done with the explanation without numbers here, it's not so easy to do this. And so you could argue that why don't you just do a general purpose analysis? But Alan would argue they had some advantages